Greetings, programs. In this video, we're going to see if we can get this AC inverter working off of our 12-volt accessory computer interior standard car battery off of this 2019 Chevrolet Bolt HV. And we're going to also do a quick review of the high voltage components here in this vehicle. And we're going to start with the traction motor and kind of work our way backwards. And a quick shout out to the Weber Auto YouTube channel, because they pretty much tore apart this car, and everything I know about the Bolt's components are from that channel. So the drive motor is down here somewhere. We're not too concerned with that right now because we want to use the battery pack to drive home appliances. But the drive motor comes into this unit down here, and that is called the SPIM. That is the single power inverter module, and I am reading off notes. Here's a quick summary of the notes if you want to just see those. So we're looking at the SPIM single power inverter module, three-phase inverter to run the drive motor. It takes the 400 volts off the high voltage system, which you'll find the 400 volts off of a lot of these orange cables, and you don't want to play with those. It'd be cool if there was a kit that would hook up to the 400 volt high voltage pack and just give you tons of current to be able to use all the power out of the pack. But that doesn't exist today. So we're going with the low-tech version, backed up with a really cool kind of backup system here. Alright, so after the SPIM, which is where the AC goes to the motor, the DC comes in here. It goes out three-phase AC to the motor, which is 150 kilowatts on the motor. We come up to this guy here, which is the high power distribution module. Basically, this is kind of the power router. Your battery power comes here in the back from the battery pack, and it gets routed to the various places. This thing on the front is the direct DC in for the high power level 3 charger. So this goes to this cable goes to the charging flap, where direct DC goes in for the fast charging. And then this box down here is the AC kind of lower level charging. So it's the level 1, level 2 AC input from the charge flap. Comes in here on AC, gets converted to DC, which then comes up here on one of these, I think. It's kind of a lower power charging mode. And what we're concerned with is this guy right here, which is the accessory battery charger, and step down in voltage as well. So it takes the 400 in, this guy right here, and then outputs the 12 volt DC. Here's the negative terminal for that. And can I locate the positive terminal for it? Yes, that's right below it down here. Right here, which goes up to our battery, which is what we're going to be hooking the inverter up to. Internet research shows that theoretically this thing can pump out 1600 watts is our max for charging the battery. So we need to be cautious of that as far as, like, if we don't want our battery to drain completely over time. You want to keep it under 1600. And then there's also limits on the components that we're going to use, which we'll take a look at here. Here's the inverter I chose. It's an Ames Power unit, company out of Reno, made in China. It is a pure sine wave inverter. You can look up on the internet what the difference between a modified wave versus a pure sine wave. I went with pure sine wave because we might want to run electronics, and just you get a better AC signal off this thing. So a little more expensive, which means I kind of had a dip in I had to lower my max wattage to fit within budget, which is fine because it's still 2000 watts continuous, 4000 surge, which is more than we can get off of this 12 volt system anyway. So that's fine. I got a little bit of a larger than what we could do in case I wanted to use it for other purposes or have other battery banks or solar or whatever. So a little bigger than what we need. Battery cables are also smaller than what we could pull max. So one useful search is looking up the kind of the current you can pull off various wire sizes over distance with voltage drops. So we're going to go with a 3% voltage drop. We're not running critical loads, but we're just going to keep with that because we're not going very far with our DC. This is the DC side of this connection. So here's our AC side. Here's where our DC side is going to go. So this thing can do a max of 200 amps on the input side. We're not going to get anywhere near that. We're going to do, these are 2-gauge cables. And if we look, we can do 120 amps max off of a 2-gauge cable, which is right here. And that's up to 15 feet if we want a 3% voltage drop, even further if we were fine with a 10% drop. So that's fine. That's good enough. Okay. So what other safety issues should we talk about here? The other thing that I don't have at the moment that I will need to add is you want to fuse. You want to fuse your cables always. And I don't have one of those yet. It'd be something like this guy, a 100 amp fuse, or something like this that you would see in like a custom car stereo. You know, making sure that the cables you buy can actually fit in these connectors. Okay, so let's go ahead and get started on hooking this inverter up to our standard car battery. Not too big of a deal. We've got our trusty 10 millimeter, and that's what's going to go on here. And we're going to do our negative first, of course. So we go ahead and put a mat over our workspace here to set the inverter on. Keeping in mind that we may have some heating components in here that we just need to be cautious of. We've got like a battery pack coolant heater system. We've got a cabin heater system, which isn't in use. And we've got a electronic components heater as well. But we'll check all that when we get this system up and running. There's some resistance on this bolt. Not sure why. Maybe it's not meant to come fully off, so it's all stiff at the end. Alright, now we've got our negative terminal off, so we can safely work with the positive side of the battery without hitting the chassis of the car and causing sparks, which is always good. Still, we'll be careful with this. Always be careful around electronics and batteries. There's a lot of energy stored, even in the standard car battery. Don't have to worry about the high voltage battery pack. It's shut down at the moment, and you know, it's got safety features. So, and it's good we disconnected the negative, because even when we go to put this wrench on, there's a very small clearance here on hitting the chassis of the car, which is not good. Again, I think these aren't meant to come off because they're really stiff at the end. They're just meant to loosen so you can remove the terminal, but we're going to do more than that. Alright, we are ready to connect our positive side cable here. Snug this on. Now I pulled both washers out so that the terminal of this cable is flat to the input. That way you get the best connection. We don't have, we don't have a huge surface on these terminals that we're going to have, like the battery cable connector itself. So it's good that we're kind of setting our limits to that 100 amp limit, because there are some current limits in our components here that we're using, regardless of what the inverter can do. Snug that. We've got our positive connected. We're going to work on the negative here, connecting the system back up. Keep in mind we have a live 12 volt connection right here, and the chassis is going to be energized again. The car is going to be ready to go once we hook up this negative terminal, and we're going to hear some noise come from the computer systems as they boot up. So let's go ahead and put our negative terminal on. That's to be expected. We're going to put our negative cable on here, keeping in mind that this is all live right here, and this is all live right here. So keeping that in mind with our tools. In fact, I might just go like that. That way, if I'm swinging this way, we're just avoiding that risk. What I'm going to be adding to this system is a fuse for the positive cable on this system, or upgrade to bigger cables. Find a better way to connect them directly to this 12 volt battery on the terminals as a whole, while still allowing the charger from the high voltage battery pack to reach the battery as well. That'd be the improvements that I do on this system. A little bit. Okay, and our negative terminal is down here. Alright, we've got our negative battery terminal here connected to the battery, the 12 volt battery of the Bolt. Still, we're not working with the high voltage battery pack, unfortunately, though there are a lot of different safety concerns with that system. Alright, we're going to connect this up to the negative terminal here on the inverter. Be careful, you have a live 12 volt system here on the other side. Snug it. What we have so far is two 12 gauge DC, 12 volt DC cables coming from the standard DC accessory battery in the Bolt. And we're going to these terminals, input terminals on the inverter. Here's the back side for the negative. And we also have something else here too that we want to hook up, and there's a ground. This is probably for the chassis itself, and it could be for the GFCI system to work on this AC outlet. So we're going to connect just a wire. In this case, this is a power cord for like a network switch or something. We're going to just use the ground wire. Just found a place on the car that is chassis ground. We're going to use the this is a 10mm bolt right here for this reservoir, and it is connected to a bracket that's connected to this heating system here. We're going to wrap one end of our AC side ground, chassis ground. That just gives us a ground for the inverter chassis itself. And this system should be good to go. We're going to go ahead and power up. So kind of an overview here. Things we need to be worried about are our heat coming off of this thing. It's on kind of one of these moving mats. We may want to move this if it gets too hot. And we want to keep an eye on the power that we're pulling out of this inverter. So we can pull out more power than these cables or even this battery can provide over time. So what I've got here is a watts up meter, which we're going to plug into the AC output and then run our extension cord to our appliance, which in this case is going to be a refrigerator as our test. All right, what else are we looking at here? So we got to keep an eye on this guy. That's our 12-volt battery charger from the high voltage pack right here. We got to keep an eye on, you know, our cables and our temperatures there. It does have fans in the back. So yeah, let's go ahead and turn the system on. And we're gonna want to make sure that we have all the accessories off in here. Like, I don't want to run the heater or anything. So we're gonna power up. COVID-19. Yep. Turn the radio off. All the heating and AC systems are off. Car's good to go. Turn off the headlights. And we should hear the whir of systems operating. I don't hear any of the cooling systems for the battery pack or anything. Those are running. So after some exploring here under this, the battery pack coolant system is running. That's what that whirring sound is. You can see the reservoir being pumped there. So our high voltage battery pack is doing its job. We've got our watts up meter plugged into the AC inverter. And we've got an extension cord plugged into that. This extension cord runs up to the refrigerator. Refrigerator's open, so we can get it to run. Right now we have nothing because there is a small, like, digital button here for turning on the inverter, so that it kind of waits and does a self-check. So let's turn this on. Gotta hold it a little bit. There we go. Got a green go on the AC output side. Letting the refrigerator run for a while, we have some max numbers here on the the watts up meter. Currently we're running 3.28, and if we look at our max, the peak load on this refrigerator is about 10. So that's kind of about what I'd say our limits are on our current setup, with mainly this 2-gauge wiring being the weak point in this system. You know, the battery pack in the Bolt is a 60 kilowatt hour pack. The refrigerator, I found an expensive refrigerator online for about $2,000, saying that it was 65 kilowatts per year, which gets us down to 86.19 watt hours per year. And if we divide 60,000 watts by 86.19, that's 696 hours or 29 days. So this car, not at its current charge because it's not fully charged, and you lose, you're not going to be able to drain the entire high voltage battery pack. But yeah, we're like at 29 days with just a refrigerator. That's kind of cool. So if we look at our output side, given the sustained 16.66 amps, which is the 2,000 watts sustained at 120 volts, it actually should say On here on the output side, 17 amps is our max. Yep. So given that we have a 100 amp limit on our cabling here on the DC side that we've set ourselves, you know, we're not going to be able to pull that many amps. So if we take our 100 amp limit on the DC side and do a little calculation here, we say 100 amps times 12 volts, 1200 watts, and then if we divide that on the AC side, we divide that by 120 volts, and it gives us about 10 amps that we can safely pull from this whole system here. So, you know, maybe subtract 10% from that, just from losses and kind of a safety factor. And, you know, we could probably pull about 9 amps total on this system for a total of about 1,000 watts, which is a good rule of thumb to kind of use on this system. Nothing will get hot, and our cabling will be fine. And, you know, we've got a pretty long extension cord here too, so there's going to be some safety factors we want on our, you know, the age of the connectors on the AC cables, and the current draw over the distance of this extension cord as well. So yeah, pretty good system if I need to use it, which currently I don't, which is cool. All right, thanks.